Your AI assistant needs to handle multiple conversations at once. But how do you keep each thread state perfectly isolated while still sharing relevant user context across all of them? We'll implement LangGraph's dual persistence system that combines thread-specific checkpoints with cross-thread memory storage. You'll see exactly how to compile a graph with both a checkpointer for conversation history and a separate store for user memories that persist beyond individual threads.
From LangGraph, checkpoint, memory import InMemorySaver. Hash, we need this because we want to enable threads conversations. Checkpointer equals InMemorySaver. Hash, define the graph. Hash, compile the graph with the checkpointer and store. Graph equals graph. Compile checkpointer equals checkpointer. Store equals in-memory store.
This demonstrates the persistent state pattern for workflow orchestration, where execution state is automatically checkpointed at each step to enable resumption, inspection, and branching. The pattern treats workflows as state machines with durable memory, allowing you to pause, rewind, or fork execution while preserving context. What makes this distinctive is its separation of computation, logic from persistence concerns, enabling features like time travel debugging without modifying your core workflow code. The approach works by instrumenting the workflow engine to emit state snapshots at every transition, storing them in a thread-specific timeline. Checkpoints capture not just data but execution context, including pending operations and error states, while the memory store handles cross-thread persistence for shared context like user profiles. This dual-layer design keeps workflow logic stateless, while the infrastructure manages persistence, enabling features like human-in-the-loop approvals or fault recovery without polluting your business logic. This pattern solves the problem of ephemeral execution in complex workflows, where losing state means losing work. It's essential for long-running processes, interactive systems, or any scenario requiring audit trails and recovery. The trade-off is storage overhead for checkpoints, but the benefit, resumable, inspectable, and branchable workflows, justifies it for stateful applications like chatbots, approval pipelines, or multi-step data processing. Let's break it down.
From LangGraph, checkpoint, memory import InMemorySaver.
Imports InMemorySaver from LangGraph to handle thread state persistence in memory, a temporary, non-persistent storage solution for maintaining conversation context between graph interactions during runtime. This is purely for in-memory state management. No TTL or platform-specific features are configured here.
Checkpointer equals InMemorySaver.
Instantiates an in-memory checkpointer for conversation state persistence. This enables thread support in LangGraph, allowing the graph to maintain separate conversation histories for different users.
Hash, compile the graph with the checkpointer and store. Graph equals graph. Compile checkpointer equals checkpointer. Store equals in-memory store.
This code compiles a LangGraph workflow with an InMemorySaver checkpointer to enable thread-specific state persistence. The checkpointer parameter tracks conversation state using the threaded from the config, while the store parameter, though undefined in this snippet, would typically reference the same memory store for consistency. The compiled graph now maintains state between invocations for the same thread. LangGraph state persistence. The InMemorySaver checkpointer enables thread-based state management by saving conversation history between graph invocations, while the compiled graph maintains execution context across nodes. Thread IDs must be unique and consistent across invocations to maintain state continuity, as mismatched IDs create orphan sessions. This pattern transforms stateless function calls into persistent, conversational workflows without manual state handling.
The threaded remembers what the checkpointer forgets to store.